Yeah, welcome everyone to High Performance Computing. Now we have our real lecture 1. So the last one that you maybe have seen, the practical lecture 0.1, was just a warm-up for those that didn't have experienced Unix before or that really didn't know about anything what is related to SSH, the secure shell. But that should be basically in the pocket of every computer scientist usually. But because we have the Bologna situation with universities, sometimes we have people doing degrees in computer science, having maybe done biology before, chemistry or anything, and maybe didn't have that knowledge. However, today we will start with a real, let's say, overview lecture. Again, we will do different pointers and motivate a bit the material, why we include several aspects in the course. But before we go into the material of this lecture, let us review a little bit what we had the last time. And this was basically the idea of understanding that HPC today and all of these clusters that basically constitute HPC, we will learn a bit more what's the difference between a supercomputer, what is HPC, what is a cluster, and so on. They all run Unix systems or Linux derivatives of some sort. So in the other words, if you have knowledge about Unix, roughly, you need to be not the perfect expert, but if you have knowledge about Unix, you basically tackle them all and you can use them all. There are basically some elements of it which are very important to understand. Firstly, the remote aspect, right? You leave basically always your laptop when using it. Hence, you can operate a Windows laptop like I do, because my Unix and my Linux is always on these nice, beautiful horses here, right? So they have powerful, they have a lot of memory. I don't need my laptop for programming. So hence, remote is an important factor. The other thing that you basically have seen with the Euro HPC supercomputers, right? The 10 or 12 we have right now, and all the smaller clusters in universities, test clusters and so on. Usually as a scientist, you would not use one, right? You would use many of them. You get computational time over time, basically for different grants on those machines, on these machines, on other machines. Hence, you will port your code usually in a HPC world from one machine to another where you get time. But if you then master Unix at that level, basically, then you're also basically very safe in one respect. The other respect is the software. So this is also what we tackled last time, if you remember a little bit, these modules that we discussed. So this is a way of how administrators usually provide scientific software. Computational fluid dynamics codes that we will learn from Razor, for instance, with ANSYS is one example, OpenFoam another, but also simple things like Python, right? I think everybody of you knows what Python is, I hope. Yeah, good. Right, so, and you have seen the list is endless. And this is also something which is very common in HPC. You would basically use the systems there where also your software is. Not all software is necessarily on all the systems. It has something to do also with the architecture of the system. Is the architecture supporting your code to a very good degree? One example is, for instance, deep learning packages. If you do artificial intelligence and then you're just on a cluster with CPUs, that's really not the idea, right? This is the wrong cluster for doing AI. You need to be on a machine where GPUs are. For those that don't know the difference between CPU and GPU, I will come to this today, right? We will discuss it a little bit, but this is an important factor. Finally, what is also important to realize, you have one ID on your laptop, but in this supercomputing world, you have IDs on different machines that are basically not connected to each other, right? You have seen on the deep test cluster, I was Real 1, on the other cluster, I was Morris. So they are basically complete separate from each other. So what you do on one machine will not influence what you do on the other machine. And this is another part of it. We have seen, however, that the access can be provided in a way that you, for instance, use the same key, right? The public-private key, that was the second part of the lecture. And this had to do something with the remote access again, and most notably IT security. So many of our systems have been hacked a while ago. So this security has been much more, let's say, intensified and bettered. And we have seen the key ingredients of SSH if you want to access the HPC machines is really the three things. You have a remote host name. It's a little bit small to see here. Sorry for that. But you have the slides, of course, online. You have a remote host name that was, for instance, a deep machine at FZ Jülich, or it was Elia at HI.is. And then you have to specify your username. The username is something that the administrators will give to you, right? Also in this course, we will give the accounts for you. So we will have all usernames together. So you don't have to care about that. What you have usually to care about is your private public key pair. And we have seen on the earlier page, there was a nice description how you do SSH key gen, and this will be part of your assignment to try it out yourself. But once you have the keys, there's one important concept, because that is always done very wrong every now and that is sharing the private key. That should be never done, right? The private key should remain on your laptop, on your desktop. The only thing that you share is a public key. Hence, you would have a username, you would have the remote host, whatever HPC system it is. And as you uploaded the public key or gave the public key to the administrator, you have the matching private key. And whenever you want to do an SSH connection, which is sort of indicated here in this funny little graphic, you can present your private key and no one else has this. That's why you should not email it around. You should not put it on your website. It should remain your private key. And with this, you're then basically getting an SSH connection and are able to log in basically and then perform here, for instance, the hostname command. Then you can really see, okay, I moved to another system, right? Here's the deep system. Here's the eHPC at the HAUI location. So if you want to learn more about it, there's lots of documentation on the earlier page. You can access this from UCLA under HPC. Again, questions for logins and so on. I know you have maybe some that will come as part of your assignments. So don't worry, we will equip you with accounts. And this was really what we had basically most importantly in the last lecture. So let's move a bit ahead what we do today. And this is really the first, let's say, overview lecture over the whole course again in a way, and also clarifying some terms, terminology. What is high performance computing? What is a supercomputer? And so on. So we start with a couple of building blocks which are very important and why HPC is very related to scientific visualizations, engineering applications, and so on. We will clarify the top 500. That's a very important list today. It basically, of course, as the name suggests, has the top 500 supercomputers in the world that we know, right? Who knows what the Pentagon has in his cellar? But let's say the military ones we probably don't have, but many of the civil-oriented ones or that we're known from companies are basically listed there. Then we have certain terminologies that are not maybe so obvious to you. And this is multi-core versus many-core, for instance. We will clarify these terminologies, also why we basically need shared memory and distributed memory architectures and what the balance with them and what the challenge really in programming them. Hence, we come to something called hybrid architecture, which is mostly in use today. But this also constitutes huge programming complexity, what we call parallel programming, right? So you have to really think about different processes at the same time or different threads at the same time, as we call that in shared memory. And this clarifies already a lot of terminologies which are important. Then to the ecosystem technologies, again, we will review the many core GPUs. We will make a case for artificial intelligence and deep learning. We will not cover that much today, but you get a little bit of flavor why GPUs and deep learning belong together, really, and why CPUs are not the kind of choice there. And then we look a little bit in the broader ecosystem. What is our competence center here in Iceland? Why we call it supercomputing co-design, so new architectures, why it's still research, this HPC. And at the end, we will look a little bit on the large-scale infrastructures and, of course, some emerging quantum computing that we also do in research right now. So quite a broader, let's say, lecture in terms of topics, and we'll give references to future lectures. But it's important, I think, at the beginning of the course to get really your 10,000 overview, right? Where HPC is in the larger field and how it relates also to the core building blocks. Afterwards, you basically have definitively ideas of the latest developments in parallel processing and HPC. And most notably, we will understand racks, and we understand a CPU, a GPU, and put them all together, and then creating bigger machines, as you see more in this terms of racks. So how we basically create these aspects, and then, of course, a modular approach, which is then even bigger, leaving the racks to different sort of technologies. With this, there comes also complexity in parallel programming that we will pick up with distributed memory, shared memory programming, and so on, which will be also part of the next couple of lectures, right? So we motivate this here. So let's start. What are supercomputers? What is high performance computing? They are often used at the same time, right? From the terminology perspective. We have seen in the last lecture already the list of Euro HPC supercomputers where every one of you has basically access to it. You just have to write a computing proposal and then you will be judged if you can get access or not. As I said, Bitcoin mining as application is usually not a good idea. But when you have, let's say, a scientific application, building a bridge in Iceland, for instance, and you want to first simulate it, then, for instance, you just get computing access. Here's LUMI. It's also a very specific system for Iceland because we are part of the consortium. This is basically 10 countries that finance LUMI. Iceland has a small share, but still Iceland is part of the LUMI in Finland. Hence, when you look at it, these are very big, bold machines. And what we usually say a supercomputer means at the forefront of computing, right? We call it sometimes a Formula One. Sorry, I'm a bit back to you. But Formula One of computing, because we always integrate the newest forms of GPUs, the newest forms of interconnect, the newest forms of CPUs. And that makes it really still a sort of matter of research because nobody has done this, right? So we have now NVIDIA Hopper cards, a very new architecture of NVIDIA cards. This needs to be integrated. Nobody has done this maybe at the scale before. Hence, it has a little bit this research flavor still of saying, especially supercomputers, not all HPC machines, but supercomputers are those, let's say the top 500 we will come to in a moment where these are part of from the Euro HPC joint undertaking. These are the ones that we would call then supercomputers, while HPC machines would be, let's say, also smaller clusters that are in the university, like the deep test cluster or our ELIA system. When you now look on the HPC, we have looked at this already a little bit on the emphasis on interconnect, right? So that these parts, all the racks that you see here, are extremely well integrated with each other with, let's say, InfiniBand interconnect, which is, let's say, one definition of sort why it's HPC. And it has then a cover of what we also will cover in this course, but it covers really different architecture parts, theory, technology, and software. And we will go a little bit in all of them a little bit. You will see that lots of theory is a part of physical models when you want to do scientific applications, how an airplane flies, for instance. You would have numerical laws that we use there. Then for technology, we have different types of really CPUs, GPU architectures. We will really look at this in the course. Then also think how this relates to big data storages, but also the interconnects, networks, as I suggested. So technology plays a big role. And as I said, we usually adopt technology which is really, really fresh, right? The cutting edge. And that makes it sometimes a bit difficult. Architecture-wise, we have some common, let's say, understandings. Shared memories has limits, but it's extremely fast because, you know, basically you access directly the memory. But distributed memory has to be the modus operandi because you have very large systems. And again, the interconnect then to transport data between the different cores and all of these architecture aspects, how you really plug these systems together will be an important part also today. And then software, not forgetting this should all run, right? So SSH was just one part of it. We have scheduling, we have monitoring, we have libraries, as we have seen in the module environment. They all need to support parallel computing. It doesn't help us to have a Java application, just run this 5,000 times on all the different GPUs, and then we have a parallel application. That's not going to work. The application itself needs to be parallelized, right, to work in parallel on all the different machines. And what we also add in this course a little bit as a practical lecture is that I will show you how to get access to these systems. So once you leave the room here and hopefully maybe graduate at some point in time, that you know you really can use your HPC JU systems also once you have a really, let's say, scientific engineering application. Again, revisit again what I mean with network interconnected was a bit short. Again, HPC, these clusters have very specific interconnects from, for instance, in the past Mellanox, which was recently bought, but it doesn't matter. Just to understand that really these different cores, the different technology inside these clusters can communicate extremely fast, right, with low bandwidth with each other. And that is important when you have, let's say, lots of physical applications, but also we see why in AI that's an important part. MPI and these things are still also used in deep learning, for instance. And HTC is something which more and more evolved to cloud computing. Again, we had already discussed this in the prologue of the course, but this is important to understand that here the interconnect is not as important. Hence, you cannot use these systems basically for weather forecast, right? There are lots of neighboring aspects or a crash of a car that you want to, let's say, have as a parallel application because you need the communication a lot. Here, you would rather say you have maybe 2 million documents, newspapers, and you want to get out all those that have a sport article and write something about a specific, let's say, sports guy, or as we have heard here from this Icelander that is out of the door, the first and only one that was in space. If you want to have his name and you look him up in all newspapers in the world, then you can do this embarrassingly parallel, right? You use these newspapers, you chunk them up, you evaluate in all of them separately is actually a mentioning of a name. And at the end, you summarize and say, okay, this Icelander was in so and so many newspapers. Hence, a different architecture. We will talk about this in the cloud computing course much more. Yep. Bringing us a little bit now also with this interconnect, what we discussed here, now how we actually now start to use all of those in parallel, right? Obvious as we think about that these are all now on, right? Then basically the CPU or GPU, it doesn't matter in the moment. We have a process that is running in a timeline, right? So it's just running, it's alive, it works on its own. It has nothing to do at first with the others, right? It doesn't even know that I'm actually running next to it. So hence, this is what we call a process. It's running on one of the processors like GPU, CPU, etc. Could be a core. And the idea now is that we want to make these processes work together, right? Equally, when you would see a football team, soccer team, whatever, we want to make them play together, not only running alone in the field, right? Or handball, I think that's much more prominent because this evening is an important game in handball for Iceland, right? So fasten your seatbelt for this evening, but we hope they do a lot of good parallel processing, right? They want to work together. They want to throw the ball not always to the goal on their own. They want to basically pass and so on. But this is exactly what we want to do with parallel processing. This is not easy, right? You see that sometimes in the performance in handball as well as on the parallel programs. It looks easy here if you have just 5 processes. But if you have our large HPC applications, we're talking sometimes about 10,000 processes, 20,000 processes and more. So it's hard to easily also make them communicate, and we need software and tools and technology to really do that. Then the speed that we really can achieve then based on these systems should be also a little bit on the performance of each individual one, but also how they solve a problem in a cooperative way. And this sort of cooperative way, you see this here also, is an important part why we call it parallel computing. And this is something which we will also have in lecture 2, lecture 3, lecture 4. The beginning of the lectures will be all about it. Now thinking a little bit why we do this. Now you would say, well, what's the benefit, right? And you see here maybe a couple of nice simulations. Here you can mention, this is the Eyjafjallajökull volcano in the past, right? So all of these, what you see here are quite processing intensive applications, right? So creating turbines before they ever see a real construction engineer that is building them, they will be all simulated in a computer. The design, the materials, and you see different stress under different, let's say, velocities, and also the aspect of a kind of turbulence which will come out of the turbines. All of this will be today used in HPC, in high performance computers. These are different methods. One of it is here, these very famous one, numerical methods based on known physical laws, but there are many others. And more recently, also we have artificial intelligence, right? More data-oriented problems. Lecture 7 will be all about it, where we talk about land cover maybe and remote sensing to identify this. All of these are really large-scale problems where your laptop is not anymore really the kind of choice. And the scientific visualizations often go with it, right? You will see that this really demonstrates usually why HPC is needed. And it is also nice, let's say, understanding, because if you have suddenly, let's say, 10,000 processes working on the turbine, you also maybe want to understand different aspects. Like here you see a little bit the mesh, which is an important topic that Reza will also explain a lot. You know, you mesh out essentially a kind of area that you want to compute, and then each little mesh is parallelized in a different computer. And we will see how that materializes over the course of the lecture. This just give you an important factor that scientific visualizations are usually very important and should go alongside it. And for this, we have usually a discretization. Let it be a mesh like you see here in the Formula 1 car to understand the, let's say, airflow, or as I said here, the one for the aircraft. One that is also very good in understanding is the 3D kind of blocky idea. Let's say this could be somewhere in Bolungarvik, the Bolafjord platform, and the people will understand what basically wind is coming there or what waves we can expect on the front there at some of the shore. You would basically crunch it down in different pieces. We call this a Cartesian 3D grid maybe, and then would actually compute the physics in all the different pieces. And every time step, you would basically now exchange data between these different tiles and recompute. And that's basically the basic principle we will talk about in lecture 2 and 3 and 4 and so on. But then in this idea, you solve it in parallel over time. And this over time is again alluding to these visualizations that we see here, like a blood pump. It matters not which basically scientific visualization you have or which field you have in particles. This time step is an important factor. You compute something for a very specific point in time, then you usually exchange data with your other processors, right? And then you recompute, let it be a physics formula or something else. So hence, again, visualizations help you a lot really to understand this parallel computing a bit more. Most notably, I think, is this or that. And we will take care of this one more in detail later on in the course, and we'll basically see a little bit how you could potentially create a fishing simulation with boats floating even maybe on top of the ocean, and how would you compute this. But in the beginning of the course, we give several pointers. So this will be something we establish in lecture 2, 3, 4, with message passing interface and so on. Let us come again a little bit back to high performance computing. The top 500 number is basically something which you should also know. It helps also to understand a lot. So we have here a frontier. You can't really see that properly from, at least here, it's hard to see, but you have the slides. That is the first exascale system what we have. Then we have here Lumi and Leonardo. So you have learned that already in one of the lectures. That's our system in Finland and in Italy. And these are Euro HPC systems. But the rest is really United States, United States, United States, United States, etc. There's a small exception in Japan. And we are, let's say, in Europe these days also have to pull together money more and more to get into the top 500. Jewels, that's a system here in Jülich. In the meantime, I think number 18 has already dropped, right? And why it's dropped, it's basically updated every half a year. We update the list in June and November, in June and November, every year. What are the type 500 systems? And you really note that these systems quickly, in a way, go out of date, right? So this means, again, this top 500 supercomputers, cutting edge computers, new GPU architectures, more energy friendly, which is also something you see in the amount of kilowatts that are used in these systems. However, you see also that Jewels is still number 18, so it has a role to play. It's not a Euro HPC system, but it just is an incarnation. That's why I bring it here a little bit on these kind of modular supercomputer that we also will use basically with the deep system. It's just the bigger scale, a real big system. And I brought you also a video to understand a little bit the Jewel system. Now, what the list offers is not only, let's say, who is the top notch, here's the top 10. It also offers you an understanding what are the technologies and the hardware manufacturers, right, that are kind of very, let's say, strong in that field. You see Lenovo, for instance, HPE. Eviden is something what we called Atos Bull before. They changed name. And then you see also maybe, for instance, accelerators. So what are the most accelerators used? And I think there is no surprise. NVIDIA, 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 right? So that's very clear. But of course, NVIDIA has many different architectures in itself, right? We've seen here the Pascal Ampere architecture, Volta architecture. Interesting enough, there was no Hopper yet. Oh, no, here's one Hopper, exactly. So this is a no cutting edge architecture of NVIDIA, still very small in the percentage, but it shows you a little bit also the technologies that are adopted in the top 500. So for us, it's very important to understand. There's different NVIDIA cards and so on. We will look in lecture, I think 6 around it. So what does it mean to go from a Tesla or basically going from some Ampere architecture to a Volta and so on, and also Hopper architectures. This will be coming in later lectures. But you see clearly it's a really heterogeneous amount of technologies we integrate. Now, how is this top 500 built is a little bit controversial. So for once, of course, it means lots of money. You see US, yeah, lots of money, lots of machines. But there's a LINPACK benchmark that is also used to rate these machines. However, the problem with LINPACK is that it's basically just a dense system of linear equations that is solved. So a mathematical problem that was representative, let's say 20 years ago, but more and more, especially with the onward of AI and other applications, it becomes a little bit a question marks, right? That's why I write here critics exist. It's still the modus operandi, and the people have to measure this on the systems and then bring the results in, and that's how they are ranked. But today we have more realistic application benchmark suits as well. So this is more sort of, as we sometimes call it, also political way of inform who is the best supercomputer in the world. But you can imagine it has multi-millions of euros of US dollars. So it also influences politically who has the best supercomputers and so on. We application scientists, however, are much more interested in that ones. So there are real application mini benchmarks available for AI, for different applications in bioinformatics and so on, where the performance is not necessarily the best on the top one system, because it relates also to how much memory you have, what the architecture is, and so on, things that you will learn over the course. But that is important to realize that basically this is something which gets more, let's say, critics from the community. So coming to some basic technology, I hope all of you have basically heard about a CPU before. Good. I hope you heard about a multi-core CPU. Good. Okay. Yeah, so of course, this is just a schematic diagram. Today we have much more multi-cores, yeah, so much more cores inside. But what I want to convey is a difference mostly to many core, right? And the multi-core is basically the idea of having still our chips, which are very strong, right? So really single thread performance, as we call that, is very strong. And you have this different cache hierarchies that you usually use. Once you come somewhere from storage, it comes into your memory, and then basically over different layers of cache, this is the L, it means layers, you basically have the chance to really get quickly access to data again when you do your computation. So hence, you would have the perfect architecture. The only trouble is, because the chips are basically very tiny, the more cores you put on it, the more bit errors you have and the more overheating is happening, right? Hence, we have sort of limits of putting more and more and more in cores. When you have, let's say, this high frequency, this high, let's say, single thread performance, because of this heartbeat, if you want, from the CPU, they get extremely hot. And with this, you have certain limits that you cannot put more inside this one. Hence, we motivate later many core, where we have thousands of cores. But this is important to understand. It's an important factor that this is really the clock rates and the power and number crunches that we basically have, the CPUs with, let's say, cutting edge performance. Now, when you see that how we integrate this into the machines, this is not directly only CPU oriented. It's also oriented how you have access to memory. Hence, we have this kind of idea of distributing it between shared memory computers and distributed memory computers, because the access to memory means speed, right? And that's an important factor. But you can imagine when you have just one memory, it's extremely limited, right? You want to use a memory as much of other machines as you can, hence distributed memory. And if you use both in parallel, then we actually have the reality, which is more or less used today, hybrid systems. So this is a little bit a sort of way of conceptually show how these systems are built. right? More recently, of course, we have also compared to these, also this accelerators. So accelerators are NVIDIA GPUs, AMD GPUs, which are plugged on top of it for a different purpose, right? So this is something what we also will establish in the course step by step. And this is where we then come to this many core chips. This accelerates certain problems. So in the end, it's a programming model, and we will look at this basically in the next couple of lectures. There's OpenMP here, there's MPI here, the message passing interface, and then using in the future probably even more interesting components. We, in my research group, use now significant quantum computing, have the publications in that already, and already exploring how that works, which is completely different from what we have before. But of course, also topic of HPC and more recent architectures. The standard we're going to use for shared memory programming, and is a de facto standard, is so-called OpenMP. Shared memory means nothing else that you have one big, as the name suggests, shared memory between different threads. And the idea is that you can read and write variables from it, right? I simplify here a bit. We have a whole lecture on shared memory with OpenMP, right? Just that you understand the basic concepts. In lecture 5, we will go deeper. But here, of course, this is beautifully fast, right? We can directly have the memory access. We read variables, we write them. Obviously, we should not overwrite them. So there are so-called parallel regions that we can protect and so on. But here's different elements with the speed to it if we want to access it. Hence, we have some cache coherence protocols in place where we have a unified memory access and a non-unified memory access. Hence, it gets a bit more complicated if you create them together. Again, we will have a whole lecture on this. This is more, let's say, understanding the different terminologies step by step. So shared memory is there, and we will have a closer look for it. And here's, for instance, one where you have a unified memory access. This is a kind of core system with different layers, and they have, through the chipset, you can access the memory, every one of those, right? So this would you have as a conceptual graphic as a shared memory system, and the speed to memory access comes in really through these different layers of cache. Now here's one example where you have a CC NUMA, where you have a cache coherent protocol. Still, for a user, for you as programming it, it looks still like one, basically like one shared memory, but it isn't. So there's a memory interface which then has some coherence protocols. For us, of course, the bigger the systems are, this becomes more and more effective, right? But still is not distributed memory. That's why I bring it here also to understand. It looks like distributed memory. It is in effect also distributed, but through this, let's say, memory interface, this fact is hidden and is called shared memory to really, make it a bit more complicated. And then when you go to distributed memory, you have really a bigger system. You would say every, let's say, number of processors have a memory and a network interconnect, and then would basically have to communicate to really go to the memory. Hence, you cannot anymore as a processor access this memory without really communicate. And this communication network is now the key where we talk about distributed memory and not anymore about threads that can access a memory, but processes that have to send and receive messages. This is something what we will see in lecture 2, lecture 3 more and more. It's called the MPI, the message passing interface, where they basically then have to communicate always when they have data back and forth. This will be an important part of the course, and is basically an important part again to realize. Again, we have several lectures. If you don't understand it completely, don't worry, especially not how applications will use it. In the moment, it should just mean you cannot just access a memory of another processor. You have to send and receive messages. And that's the way how you do it. MPI standard is the one that is basically used for this. So it's a very nice programming API that we can use for parallel programming. And many of the HPC applications are programmed in MPI. Some of them are MPI and also OpenMP, right? OpenMP should be not, let's say, considered as OpenMPI. It's a bit misleading. OpenMPI is an implementation of MPI. OpenMP is a complete different standard for shared memory, right? Also important. We will take care of this in the next lecture, really. Hence, in the end, how you would do it in the big computers for weather forecasts, for these things, you would basically program shared memory within a smaller part in one node, but to go across the different nodes, you would use distributed, memory programming. So you would use OpenMP inside nodes and then use MPI across the nodes to communicate. And this is then already a form of hybrid computing, which is actually not so easy to do if you have a large scale application in science. This is often where then performance analysis, where really, let's say it takes lots of iterations to make it a high performance code, because somehow the humans in one respect have not anymore the chance to really understand what's happening if you use 10,000, 20,000, 40,000 and more processes. So this was terminology. This will come in the next couple of lectures, much more with applications, with examples, just that you really differentiate distributed memory from shared memory is important to take away, and also that there are different dominant programming standards, how you would do it in practice, right? So this is something where there are beautiful libraries, which is already perfectly supported. It has some practical implication with the mapping problem, which means depending on which HPC machine you have, you also should basically consider how many threads you use, how many processes you use, because it depends a bit on how many cores are available and so on. But this is more a practical consideration we will basically then also review. Hence, very much terminology for you, and I have a sort of summarizing video. I have to close here the video before we, the sharing on the recording here before we go ahead, because we want to upload on YouTube, as you know.